1998, the retirement of the iconic SR-71 Blackbird left a void in surveillance capabilities, creating a potential gap between the United States and competing nations. Faced with evolving threats such as anti-satellite weapons and counter-stealth technologies, a new concept emerged, one that prioritizes extreme speed over traditional stealth, challenging the norms set by fifth-generation jet fighters and projected drone developments. The SR-72, the successor to the Blackbird, is faster than the fastest planes in history, and as a direct relative of the SR-71 Blackbird, its capabilities and next-level technological components have made it unstoppable. What is the SR-72 capable of? What makes this jet unbeatable? Join us as we explore the new Darkstar that no fighter jet can beat. The SR-71, known as the Blackbird, was built to fly extremely fast at over Mach 3. It had a crew of 2, with the pilot in the front cockpit and the surveillance systems officer in the rear. The aircraft was designed to be stealthy, painted dark blue to emit internal heat and blend into the night sky, earning it the nickname Blackbird. The SR-71 relied on a combination of high altitude and speed to avoid being intercepted. Its radar countermeasures and low visibility made tracking difficult for enemy missile sites. Even if a surface-to-air missile was launched, the SR-71 could often outrun it or make evasive maneuvers. The aircraft's structure was mostly made of titanium and polymer composite materials. Lockheed, the manufacturer, faced challenges in using titanium due to cost and corrosion issues. The high temperatures during flight required unique design solutions, such as corrugated wing sections that could expand without splitting. The fuselage panels were loosely fitted on the ground, aligning properly as the airframe heated. The cockpit's outer windscreen was quartz and fused to a titanium frame. The aircraft leaked fuel on the ground due to thermal expansion, causing some inconvenience to ground crews. Red lines on the wing indicated areas where personnel shouldn't step. The SR-71's tires, filled with nitrogen and containing aluminium, cost $2,300 each and needed replacement after about 20 missions. The Blackbird landed at high speeds and used a drag parachute to reduce landing distance and minimize wear on brakes and tires. Despite its challenging design, no SR-71 was ever shot down during its service life. Getting enough titanium was challenging because the United States needed more supplies. The Skunk Works team had to find it elsewhere, and a significant amount came from the Soviet Union. They managed to get the needed titanium by using third-world countries and deceptive operations. The SR-71, made mostly of titanium, aimed to reduce its visibility to radar. Its shape and materials were designed to achieve this. The aircraft had features like chines, sharp edges along the fuselage, and special materials on its skin to absorb radar signals. They also used additives in the fuel to make the exhaust less visible to radar. However, Soviet radar technology advanced quickly, outpacing the stealth measures. Chines, which were sharp edges near the nose along the fuselage, were added for stealth. They weren't part of the original design, but were found to create vortices that improved aerodynamic performance. The Chinese also reduced landing speeds and increased stability at high speeds. These aerodynamic improvements were unexpected but beneficial for the aircraft's overall performance. The SR-71's air inlets were crucial for its high-speed flight. These inlets allowed the aircraft to travel at speeds exceeding Mach 3.2, considered its most efficient speed. The inlets had a movable part called a spike at the front. The spike was fully forward on the ground and during a slower flight. As the aircraft accelerated past Mach 1.6, the spike moved inward, controlled by a computer. This adjustment helped manage shock waves and airflow, ensuring efficient supersonic travel. During early flights, the analog computers didn't always perfectly control the spike's position, leading to issues like inlet unstart. This unstart caused problems like engine shutdowns and violent yawing. To address this, engineers developed solutions like restarting both inlets. Later, an electronic control system was added to detect and fix unstart conditions automatically. NASA also found that vortices from the nose chines affected engine efficiency, leading to further improvements. In 1980, the analog control system was replaced with a digital system called DAFIX, which reduced instances of inlet unstart and enhanced overall performance. The SR-71 had two powerful engines called Pratt and Whitney J58. These innovative engines could produce a strong thrust of 32,500 pounds when not moving. The engines were most efficient when the plane cruised at its typical speed of around Mach 3.2. During takeoff, 26% of the thrust came from the afterburner, a part that boosts engine power. The afterburner gradually provided all the thrust at about Mach 3 as the plane sped up. Air first went through compression and heating to understand how the engines worked. The compressed air entered the engine compressor, where some of it was directed to the afterburner. The rest of the compressed air went through more compression stages and mixed with fuel in the combustion chamber. After passing through the turbine, the exhaust and some bleed air from the compressor entered the afterburner. At speeds around Mach 3, the rise in temperature from the compression reduced the allowable fuel flow because the turbine temperature limit remained the same. The rotating machinery in the engine became less powerful, but it was enough to maintain constant airflow through the intake. The high-speed thrust now came from the afterburner's temperature rise. The maximum speed of the plane was limited by the temperature of the air entering the engine, which couldn't go above 800 degrees Fahrenheit. The SR-71 initially used external Buick Wildcat V8 engines mounted on a start cart to start the engines. Later, a quieter pneumatic start system was developed for main bases, but the V8 start carts remained at landing sites without the pneumatic system. The SR-71 had different options for fuel, but it mainly used JP7, which was challenging to ignite. A substance called trethylborane was injected to start the engines, creating high temperatures needed to ignite JP7. The TB produced a green flame during engine ignition. During takeoff, the SR-71 carried only a partial fuel load to reduce stress on brakes and tires. It quickly reached high speeds and altitudes, using 1/3 of its fuel. There was a misconception that the planes refueled shortly after takeoff due to fuel leakage caused by sealant failure, but the real reason for refueling was the aircraft's need to achieve maximum speeds, which were only possible with aerial refueling. In-flight refueling was necessary for long-duration missions, and specialized tankers such as the KC-135Q were used. These tankers had modified high-speed booms for refueling the SR-71 at high speeds. The aircraft's cockpit had a special display for the pilot during refueling, providing subliminal cues on aircraft attitude. For navigation, the SR-71 used an astro-inertial guidance system developed by Nortronics. This system tracked stars through a window on the fuselage, correcting navigation errors with celestial observations. The navigation system was accurate enough to limit drift to 1,000 feet off the direction of travel at Mach 3, according to a former SR-71 pilot. The SR-71 had various tools and systems for its missions. These included optical and infrared cameras, radar, and electronic intelligence systems. The cameras could be placed in different parts of the aircraft to capture wide area or close-up images of the target. The radar systems were later replaced with more advanced technology. The aircraft also had countermeasure systems to protect against threats. These electronic countermeasures could jam signals and confuse enemy systems. The crew used specialized suits to withstand the high altitudes and temperatures during flights. They couldn't use standard masks, so pressurized suits were made to provide enough oxygen. The cockpit had a cooling system to manage the extreme heat generated during high-speed flights. The crew also had a way to get food and drink during long missions, using containers with straws that they could guide into their helmets. Overall, the SR-71 was equipped with various technologies to successfully carry out its reconnaissance missions. But in 1989, it was retired. People thought the SR-71 Blackbird was retired in 1989 because it was costly and considered unnecessary due to other improving reconnaissance methods. The Air Force stated this to Congress. However, some believed the decision was more about politics within the Pentagon than the actual need for the aircraft. Graham, a former commander, argued in 1996 that the SR-71 had unique intelligence capabilities not provided by alternatives like satellites, U-2S, and UAVs in the 1990s. He pointed out that in the 1970s and 1980s, commanders of SR-71 units were often promoted, but by the mid-1980s, a new generation of generals wanted to cut the program's budget for other priorities, like the B-2 bomber. These newer leaders believed the SR-71 was no longer essential and tried to convince Congress and the military services of its redundancy, even though Graham argued that their claims were more of a sales pitch than a fact at the time. The Air Force might have considered the SR-71 a bargaining tool to protect other important projects. The generals in charge didn't see the intelligence provided by the SR-71 program, which was crucial for operations and strategy, as very valuable for the Air Force. Instead, they believed it was more important for the CIA, NSA, and DIA. A misunderstanding about aerial surveillance and a lack of knowledge about the SR-71 fueled efforts to discredit it, with the promise of a replacement being developed. Dick Cheney mentioned to the Senate that the SR-71 cost $85,000 per hour to operate, but opponents estimated its support cost much higher than it was. Although the SR-71 was superior to the U-2 regarding range, speed, and survivability, it lacked a data link that the U-2 had. This meant the SR-71's data couldn't be used in real time and had to wait until it returned to base. This limitation was used as a reason to shut down the program. Some argued that the lack of upgrades made it seem obsolete, favoring those pushing for other programs. Attempts to add a data link were hindered by factions in the Pentagon and Congress that wanted to end the program. Despite Congress allocating funds in 1988 to keep 6 SR-71s flyable, the Air Force should have spent the money. The decision to retire the SR-71 from active duty came in 1989, with the last missions flown in October of that year. General Schwarzkopf later discovered during Operation Desert Storm that the expedited reconnaissance the SR-71 could have provided was unavailable. The main operational capabilities of the SR-71 program ended in October 1989, and the squadron closed in mid-1990, with the aircraft distributed to display locations or kept in reserve storage. Because of concerns about political situations in the Middle East and North Korea, the U.S. Congress took another look at the SR-71 in 1993. Rear Admiral Thomas F. Hall explained that the SR-71 was retired because it couldn't meet the fast-paced needs of the modern battlefield. They believed using technology to get data in real time would better suit the tactical commander's unique requirements. They were also exploring other ways to do the SR-71's job. Mackey informed the committee that they used U-2SS, RC-135 ASC, and other assets to gather information in some areas. Senator Robert Byrd and others were unhappy that a successor to the SR-71 hadn't been developed, considering it as good as the SR-71. They argued that creating an aircraft with the same capabilities as the SR-71 would be impossible in a time of limited military budgets. Congress was disappointed with the lack of a suitable replacement for the SR-71, which influenced decisions about funding imaging sensors on the U-2. They added $100 million to the budget to bring 3 SR-71s back into service, but later cut it to $72.5 million. The Skunk Works, responsible for the aircraft, managed to get it back into service under budget at $72 million. Retired USAF Colonel J. Murphy led Lockheed's reactivation plans, with retired USAF Colonels Don Emmons and Barry McKean working on the logistics and support structure. Active USAF pilots and reconnaissance systems officers who had experience with the SR-71 were asked to volunteer to fly the reactivated planes. The 9th Reconnaissance Wing at Beale Air Force Base was in charge of the aircraft, which operated out of a renovated hangar at Edwards Air Force Base. Modifications allowed near real-time transmission of the advanced synthetic aperture radar's imagery to ground sites. Bringing back the SR-71 faced many challenges. The Air Force didn't plan for it in their budget, and unmanned aerial vehicle developers worried their projects would suffer if money went to the SR-71 Ace. Congress had to approve funds yearly, making it hard to plan for the SR-71 in the long term. In 1996, the Air Force said they needed more specific funding and tried to stop the program. Congress approved the funds, but in 1997, President Bill Clinton tried to cancel the $39 million allocated for the SR-71 using the line item veto. In 1998, the U.S. Supreme Court said the line item veto was unconstitutional. The SR-71's fate remained uncertain until September 1998, when the Air Force asked for the funds to be used elsewhere, and they permanently retired the SR-71 in 1998. NASA used the last 2 flying Blackbirds until 1999. All other Blackbirds are now in museums, except for 2 SR-71S and a few D-21 drones kept by the NASA Dryden Flight Research Center. For a long time, no other plane could match the abilities of the SR-71. Now its successor, the SR-72, has been introduced. As the military strength of countries like Russia and China grows, the U.S. needs an aircraft as unstoppable as the Blackbird, and that's where the SR-72 comes in. Lockheed Martin proposed the SR-72 in 2013 as the next version of the SR-71. It's expected to be a top-notch American aircraft, possibly serving as the 6th-generation NGAD fighter, which will be crucial for air superiority in the coming decades. Unlike the SR-71, the SR-72 will have various weapons to defend itself, including guns, bombs, missiles, laser-directed energy weapons, and drones for surveillance. It will also have advanced sensors and high-quality cameras to capture detailed images over long distances. These are just a few of the remarkable capabilities of the SR-72, with more to come. The SR-72 has the potential to be the future fighter for the U.S. Air Force, equipped with advanced technologies like stealth. The NGAD fighter is designed with a triangular shape, internal payload storage, and no distinct tail section, making it the first fighter with such a revolutionary design. This design innovation eliminates the need for traditional vertical stabilizers, thanks to active flow control technology inspired by how birds fly. Although this technology provides top-level stealth, it comes at a high cost. This partly explains why the B-2 costs $2 billion. NASA invested a hefty $1 billion in SR-72 development. Congress set aside over $10 billion for the Air Force's NGAD program in under a decade, and the Navy requested over $9 billion for the next 5 years. The SR-72 is equipped with advanced sensors and weapons covering a vast area. It can detect targets, friendlies, and points of interest from miles away, sharing data instantly with the entire fleet. Instead of radar on aircraft, the NGAD fighter uses electronically configured smart skins on its fuselage, boosting sensor sensitivity, network adaptability, and remote control. The fighter features open architecture laser weapons, high-performance guns, missiles, advanced AETP engines costing over $6 billion, loyal wingmen, top-notch electronic warfare countermeasures, avionics, and communications. Despite these advancements, the U.S. knows there's always room for improvement, especially with near-peer adversaries. Hence, the fighter is designed for easy upgrades. All these elements make the aircraft estimated to cost $1 billion per unit with a top speed of Mach 6, making it one of the closest things to a truly hypersonic aircraft today. Meanwhile, in Atlanta, Hermes is working on another aircraft with similar capabilities, the Quarter Horse. The Quarter Horse, Hermes' debut aircraft, is designed to be a remotely piloted hypersonic plane with a remarkable top speed of Mach 5.5, nearly matching the SR-72's Mach 6. It's considered the only hypersonic jet with potential commercial use in the future. NASA and the Air Force are heavily invested in Hermes, contributing over $60 million from the Air Force alone. If the quarter horse proves successful, its technology could find military applications and potentially shift the U.S. military's focus from stealth to high-speed capabilities. Currently, it holds the highest payload capacity among hypersonic jets, earning its reputation as the aircraft of the future. Despite its large size, the quarter horse is equipped with a TBCC engine based on the General Electric J85 engine, known for its efficiency in supersonic space. Hermes has repurposed it using proprietary technology for hypersonic use. With about 7 units currently in possession, the engine has demonstrated success, producing 3,000 pounds force dry and 5,000 pounds force with afterburner. This allows for significantly reduced travel times, such as a New Yorker reaching London in just 1.5 hours instead of the usual 7, translating to a cost reduction of at least 450%. Hermes takes pride in the quarter horse's impressive design, focusing on hardware-rich, autonomous, and reusable systems tailored to specific requirements. This approach minimizes unnecessary components, keeping program costs relatively low. Hermes is confident that the quarter horse's test flight can be executed for less than $100 million, a notably economical figure for a hypersonic project. The Hermes quarter horse, SR-71 Blackbird, and SR-72 son of Blackbird are 3 planes loaded with all the power the U.S. has, making sure America stays ahead in the competition for super-fast aircraft. Thank you for watching. While you are still here, click the link on your screen to check out more of our videos. See you there.